Hi everyone, my name is Espen Nilsen, and this semester I've been working on my master thesis on the topic of enhanced sulfate removal and deaeration package performance at Ivar Aasen. The project has been supervised by Britt Margrethe Mollestad and Halvor Damslora, and I would like to thank them both for great support and guidance throughout the project period. The background for this project is based on the need for pressure recovery in depleting oil and gas reservoirs. Aker BP inject all produced water separated from the well fluid in their separators at Ivar Aasen, but this volume is not sufficient to replace the reservoir void that is produced. And for that reason, seawater is added. Seawater contains both sulfate ions and dissolved oxygen, which can cause scaling, corrosion, and reservoir souring. For that reason, seawater must be treated. The objective for this project is to evaluate and potentially optimize the system performance. And the method to do so is an initial theoretical phase with a plant study to set the technical frames, followed by a literature review to be able to evaluate the expected system performance theoretically, in addition to understanding the detailed mechanisms of these unit operations. And the subsequent phase is a practical phase with live plant tests intended to validate the theoretical models and the performance models, and to assess the system performance responses, focusing on system optimization. Here we can see an overview of the entire system in question. To the left we have the sulfate removal units, which is a two-stage nanofiltration system where the concentrate from the first stage enters the second stage as feed, and the permeate from both stages is mixed, and the target sulfate concentration in the permeate is to be below 30 milligrams per liter. The permeate enters the deaerator, which is a two-stage pressure vessel that shifts the dissolved oxygen towards the gas phase. The target dissolved oxygen is to be lower than 50 parts per billion on a molar basis. To be able to predict and model membrane separation, one needs to know the details of membrane transport mechanisms. And the transport mechanisms in nanofiltration is very complex, mainly because these membranes does not completely reject all salts when processing electrolytes like seawater. This induces electrostatic effects, which cannot be modeled without high-level details on the membranes in use. And for that reason, these effects are neglected, and the system is assumed to be sufficiently described by the solution diffusion model, which is used to predict how the sulfate content in the permeate depends on different process variables. Another important aspect of membrane separation is fouling. This is very important when assessing system availability, since fouling eventually causes system rundown and need of membrane cleaning. Concentration polarization is a phenomenon that's important to grasp when predicting how fouling depends on the different process variables. The figure shows this concept where a well-mixed and a laminar zone is present. This occurs due to a viscous shearing along the active membrane layer. And the figure illustrates how concentration of species rejected by the membrane changes inside the laminar boundary layer. This can facilitate fouling through depositing particulate matter or nutrients in the slow-moving regions. By employing a species balance across this domain, one can predict how concentration polarization depends on the different process variables. Henry's law is used as the basis for modeling the mechanical deaeration. And to model the Henry solubility constant as a function of temperature and salinity, the Henry-Seccheno model is employed. The theoretical performance model of mechanical deaeration is defined by coupling Henry's law to the Henry-Seccheno model in addition to a pressure to temperature and flow relation. And when it comes to the practical phase of the project, this was stressed by a main power loss on Ivar Aasen, which caused problems for the major part of the planned practical tests in this project. Some tests were still initiated, and we will have a look at some of the test data from one of these tests in the following slide. One of the tests was to increase the seawater temperature, and this showed promising results for the sulfate removal units. To the left, we can see that the sulfate content maintained below the target during the test, and on the right-hand side, we can see how the pressure drop decreased, both across the active layer and along the feed spacer, which means less wear and tear, and in addition to a marginal reduction in power consumption for the sulfate removal unit pumps. But the test needs to be reassumed to be able to conclude both for the sulfate removal units and the deaerator with respect to response on the elevated seawater temperature. At the end, I would like to state that due to these issues during the practical phase, it has been agreed with the Aker BP to continue testing and optimization after the project period. Thank you for your attention.